This is page 3 of the Matrices packet, and it will show using matrices to solve a 3x3 system using a Gaussian elimination or row echelon form, and then it will continue using the same problem to do reduced row echelon form or Gauss-Jordan elimination. So recall that the things that you're allowed to do to a matrix without changing the value of the solutions are to switch any two rows, replace a row by a non-zero multiple of that row, or replace a row by the sum of the row of that row and a constant non-zero multiple of some other row. And I'll explain a little more what that means in context. So first we're going to take this system and write it as a matrix. 1, -2, 3, 9. And I'm just pulling the coefficients off here. -1, 3, 0, since there's no z term, and -4. And 2, -5, 5, and 17. And then the goal is to get ones along the diagonal, and here in these 1, 3, and 5 spots, those all need to be ones, and the values below them, these three, need to be zeros. And the order that you want to do them in is to first get a 1 in the upper left corner, which luckily we already have that, and then below that zeros before you go on to make this into a 1, and then below that 0, and then make this into a 1, and then we'll be done. Yeah, so I'm going to rewrite the first row because that one doesn't need to change. I know it doesn't need to change because it's already a 1 in the upper left corner. So now here I want this to be a 0, and this is a nice little intro into the concept, because if I add these first two rows together, then this will end up being a 0, and you're allowed to add any two rows. I can replace this second row by the sum of this second row and another row, and I could even multiply the row by a constant if I needed to, but in this case I don't need to multiply it by anything. So here I'm going to indicate what I'm doing. I'm going to replace this second row with row 1 plus row 2, and 1 plus -1 is 0, -2 plus 3 is 1, 3 plus 0 is 3, and 9 plus -4 is 5. And then as long as I'm at it, I may as well do something to clean up this row also. So this time I have a 2 here, and I can use either one of these rows. I'm going to go ahead and use the first row. So I'm going to do -2 times row 1 plus row 3, and replace this row 3 with -2 times row 1 plus row 3. So the rule that you're allowed to do that by is number 3 here. Replace a row by the sum of that row and a constant non-zero multiple of some other row. So that is exactly what we just did. We're replacing row 3 by the sum of that row, row 3, and a constant being multiplied by another row. So now I'm looking up here, and I'm going to multiply 1 by -2 to get -2, and add it to +2 to get 0. And that's how I knew what to do here, is I did whatever it took to get a 0 right here. And then the rest of it you're just left with having to do with whatever it comes to. So -2 times -2 is 4, plus -5 is -1, and then -3 times -2 is -6, plus 5 is -1, and -2 times row 1 is negative 18 plus 17 is negative 1. All right, so now the next thing I would want to do is make this term a 1, but it already is a 1, so I don't have to do it. But if it had been a 2, then I would have needed to go through and divide everything by 2 in that row, which is sometimes a little bit tricky because you get fractions in the matrix. But in this case, we didn't have to. I'm going to rewrite the first row and rewrite the second row. Because I already have a 1 there, I didn't have to do anything to it. And now what I want is for this term to become a 0, or this element of the array or matrix to become a 0. So I'm going to replace the third row by whatever it takes. I have to use the third row, but I can use either the second or the first row. But it looks to me like it would be good. Oh, actually, I really want to use the second row because I don't want this to change. So I'm going to add these two together. Row 2 plus row 3. And then 0 plus 0 is 0. 1 plus negative 1 is 0. 3 plus negative 1 is 2. And 5 plus negative 1 is 4. Okay, I'm almost there. Only thing I need to do now is to get this to be a 1. So I'm going to recopy the matrix again. 1, negative 2, 3, 9. 0, 1, 3, 5. 0. Oh, and now, so this one here, I'm going to replace this row with row 3 divided by 2, because if I do divide it by 2, then this will be a 1. So 0 divided by 2 is 0, 0 divided by 2 is 0, 2 divided by 2 is 1, and 4 divided by 2 is 2. So that is called row echelon form, where you have 1s along the diagonals and 0s under every entry below that. And that's good because now I know that z is equal to 2 and that y plus 3z is equal to 5. So then y plus 6 is equal to 5. So y is equal to negative 1. And from the first row, I know that x minus 2y plus 3z is equal to 9. And I don't know the x, but I know that the y is negative 1 and the z is 2. And that's equal to 9. So x plus 2 plus 6 equals 9. So that's 8, 9, so x equals 1. So this part here is called back substitution. So if you put a matrix into row echelon form, then you have to use back substitution to continue working on solving it. But if you take that matrix and put it into if you want to keep going into reduced row echelon form, you would first get it into the form that we already have. So I'm just copying our work from the previous problem here. And now, after I get this done, then the next step is to change this, the value above the diagonal rows to 0, and then change these to zeros. So first I'm going to come back to here and see if I can figure out how to use some row operations to get this first row to have a 0 in the element, in the second element. So I'm going to take this second row here and do 2 times row 2 and add it to row 1. And that'll be good. I think that'll work out just fine. So I don't need to change these right now. And then Um, if I do 2 times row 2, that's 0, plus row 1, it stays 1, which is super important. If this didn't stay 1, then I would be losing all the work that I had done up above. If you do things correctly, you won't lose any of these values that you already have set up. All right, so for the next one, this is why we chose this operation here, is because if I multiply 1 by 2, I get positive 2, added with negative 2 gives me 0. Then 3 times 2 is 6, plus 3 is 9, and 2 times 5 is 10, plus 9 is 19. All right, so next, my bottom row here is good, 0, 0, 1, 2, but I don't want this to be a 3, and I don't want this to be a 9. So I'm going to replace the second row with multiplying row 3 by 3 by negative 3 and adding it to row 2. If I'm replacing row 2, I have to use row 2 over here. Notice here I was replacing row 1 and I have a row 1 here. So negative 3 times 0 is 0 plus row 2. Here, let's look at it from here. So negative 3 times 0 plus 0, still 0. Negative 3 times 0 plus 1, still 1. Negative 3 times 1 is negative 3, plus 3 is 0. Negative 3 times 2 is negative 6, plus 5 is negative 1. So this row is done. I know that y is equal to negative 1. And now I'm going to replace row 1 with whatever it takes to make this be a 0. So, and I'm going to use row 3 to do it, and since that's a 9, I'm going to multiply this by negative 9 and add it to row 1. So row 3, 0 times negative 9 is 0, plus 1, that stayed a 1. This should stay a 0, but let's make sure. Negative 9 times 1 is negative 9 times 0 is 0, plus 0. Negative 9 times 1 is negative 9, plus 9 is 0. Negative 9 times 2 is negative 18, plus 19 is 1. And so this is called reduced row echelon form, or Gauss-Jordan elimination. And because you have all ones and zeros over here, technically there's maybe a line in here, a lot of people leave that off, but these are x is equal to 1, y is equal to negative 1, and z is equal to 2. So it's more work, but then you don't have to do the back substitution. Thanks for watching.